Hello everyone, this is Dao Nguyen, and this is my individual video project for the Cyber 44201 Cyber Operations course taught by Alex Hepp at Metropolitan State University. Secure and Defend Data Cryptography. Disclaimer: this video project is for educational purposes only. I am not liable for any damages that could be caused using the information or demonstrations presented throughout this video. While I might not be able to cover every single topic related to cryptography, I will be discussing some important concepts so that you can better understand or reinforce your understanding of cryptography. In this video, I will be discussing what is cryptography, why is cryptography important, what's involved in cryptography, and then go over some hands-on examples using some tools. So, what is cryptography? Cryptology is derived from the Greek words kryptos and logos. Kryptos means hidden and logos means word. Cryptography is a science of concealing and securing a message using mathematical functions or algorithms so that the intended party can decipher and read the messages, and any other unintended or third parties are unable to decipher and unable to read those messages. In modern times, cryptography is based upon these four main principles: confidentiality, integrity, non-repudiation, and authentication. Confidentiality is about data being accessed only by authorized parties. Let's look at Bob. Bob wants to access content on a website. He goes over, enters his information, and is able to access his content successfully. If we look at Allie, who's trying to access Bob's content on a website, she goes over, uses her information, logs in, she's unsuccessful. This is because she's an unauthorized party. This is confidentiality. Integrity. Integrity is about data remaining the same. No changes are made while it is in storage or during transmission, and any changes will be detected. Let's look at Bob. Bob goes to his computer, turns it on, and saves some data. He then turns off his computer. He then later returns, enters information, and sees that everything's still the same. This is integrity while in storage. So now let's take a look at an example of integrity in transmission. Bob wants to send some data over to Rob, so he does so. Data going in transmission over to Rob. The data is the exact same as Bob sent, and this is integrity in transmission. If data were to be changed during transmission, that would be bad because integrity is lost. Non-repudiation. It's all about sender's intent. The sender cannot deny an action after it has been completed. So let's say that Bob sends some data over to Rob. Rob receives it, but later Bob cannot deny the fact that he sent the data to Rob. That's non-repudiation. Then there's authentication. Authentication is about verification and if parties involved are who they really are. So let's say that Larry wants to send some data over to Ari. He uses some mechanism along with the data so that Ari can be able to verify and confirm that the data came from Larry. Ari gets it, verifies, and confirms it did come from Larry. That's authentication. So, why is cryptography important? In our digital age, we complete most of our activities online. So we should be able to do so safely and securely. Cryptography provides us with ways to be able to protect sensitive information and data in storage or in transmission, provides us with secure communications, as well as secure online transactions. We see this in e-commerce, where you buy things online in digital stores, securely managing your passwords, securely accessing and interacting with websites, secure communications, and much more. So, what's involved in cryptography? Main parts of cryptography include ciphers, keys, hashes, digital signatures, and digital certificates. Ciphers. Ciphers are a method to convert a plain text into a ciphertext. This is encryption, and then ciphertext back into plain text, decryption, all using a certain key. So as you can see, plain text is just a regular text that you can read, and a ciphertext is after going through some permutations, makes the text unreadable. Here are some examples of ciphers: substitution cipher and transposition cipher. These are considered historic ciphers as they are no longer secure. So substitution ciphers replace each character with another following a certain key. I provided a simple example right here. As you can see, A is equal to Z, B is equal to Y, C is equal to X, and so on. Transposition ciphers, position of characters in plaintext, are swapped or rearranged following a certain key. The example that I provided down here is A, B, C, D, E, F, and reversing it would become F, E, D, C, B, A. Examples I included for substitution cipher is the Caesar cipher, where each letter in the plaintext is shifted a fixed number of positions in the alphabet and then is converted to the ciphertext. As you can see, I included the Caesar shift cipher right here. I use the default shift of 7 and use the phrase cats and dogs. Cats and dogs becomes JHAZ HUK KVNZ. So we take C and we shift it over 7. 1, 2, 3, 4, 5, 6, 7. It becomes J, and then A, 1, 2, 3, 4, 5, 6, 7 becomes H, and so on. Then we have the transposition cipher example. I included the rail fence cipher, where you take the plaintext and using a key, or also known as rails, determines how many zigzags there are. So let's take a look at cats and dogs again. The key for this one is 2, so this determines the rails. So we go zigzag. So we go C, A, T, S, which is cats, and then A, N, D, and then D, O, G, S, dogs. Then you'll take the top line and the second line, and then this on the right will become the ciphertext. Symmetric ciphers. Symmetric ciphers, encryption and decryption uses a pair of the same or shared keys. So you take the plaintext, you use the shared key, and encrypt it into the ciphertext. The ciphertext, if the receiver wants to decrypt it, will then take that same shared key and convert it to plaintext. If you look back at these two examples of the Caesar cipher and rail fence cipher, these can be considered symmetric as they use only one key to encrypt and decrypt the messages. Often associated with symmetric keys are stream ciphers and block ciphers. Stream ciphers is encryption of data is done bit by bit or byte by byte. In this example, it's just a simple example to help better understand, where it just encrypts the first bit, second, and so on. Then we have the block cipher, which is encryption of data done as bit blocks, usually fixed. In this example, I just included hello world, and you would take the first block, encrypt it, and then go on to the second. Some examples that I included for the symmetric stream cipher example is the cha-cha-20. The production of continuous key stream bits that are swayed at random, and then they will be XORed with a plaintext, which produces the ciphertext. The steps include the key generation, which includes a 256-bit key from a user-supplied key, and then they will also have a random produced 96-bit number that is used once, or also known as a nonce. Then there comes the initialization, where it sets up the cipher with an algorithm using the key and the nonce, and then goes on to encryption, which takes the data blocks and the current cipher changed after each process block. Then the output XOR plaintext with the output of the encryption step produces the ciphertext. Other examples include Salsa 20 and then RC4. It was heavily used back then, but is no longer recommended due to many vulnerabilities and security concerns. For the symmetric block cipher example, I included the Advanced Encryption Standard, the AES. So the block lengths are 128, 192, or 256 bits. There are several rounds, including the initial round, which has the add round key. Other rounds are subbytes, shift rows, mixed columns, and add round keys. And the final rounds includes all of these except for the mixed columns. All the rounds are dependent upon the block lengths. So for 128 bits, it will be 10 rounds, 192, 12, and then 256, 14 rounds. Each round makes it more secure, going through several more permutations. Other examples I included that I will be discussing is serpent and two-fish. Then we'll be moving on to asymmetric ciphers, which is encryption and decryption using pairs of keys, which is similar to symmetric, but in this case, it uses private and public. If Bob wants to send something to Rob, Bob will take Rob's public key and encrypt the plaintext so it makes it to the ciphertext. So then when Rob wants to decrypt the ciphertext, he will use his own private key to decrypt it and read the plaintext. The example that I included for the asymmetric cipher is the RSA, and includes two main parts, which is the key generation and the encryption and decryption. So in the key generation, it involves large prime numbers, factoring, Euler's totient function, and modular inverse. This produces the public and private key to use. Encryption and decryption includes modular arithmetic and public-private key pairings. There is the encryption formula and the encryption formula that I provided right here. Other examples that I included are the elliptic curve cryptography and the digital signature algorithm. Keys. As you can see, keys are an important part. This is why we need key management. Without it, there would be many serious consequences, such as unauthorized access, data loss, data breaches, and so on. Some parts of key management include generation, distribution, storage, usage. The usage is basically what we just talked about with encryption, signatures, and authentication. It also includes key rotations, where old keys are replaced with new keys, and then key revocation and destruction. Hash functions. So this is the operation that takes the data, goes through some functions, and returns a fixed length string containing numbers and letters, which is known as the hash, or you can consider it a digital fingerprint. This relates to integrity, and ideally each hash value should be unique. Some hash algorithms include MD5, SHA, and then CRC32. This next slide includes a MD5 hash generator. On the left, I have the I love cyber operations class with the exclamation point, and at the bottom, it produces the MD5 hash. And on the right is the same exact sentence without the exclamation point, and then you can see that it is a completely different output. This is very important and provides great integrity. And then there's digital signatures. Digital signatures are used to verify identity. Basically means the authentication. So it proves the parties involved are who they really are. So in this process, the sender inputs data to the hash function to produce a hash. Then they will sign the hash using a private key. This produces the digital signature. Once they send all the information over, the receiver will then use the sender's public key to decrypt and then compare the hashes to verify. Finally, we have the digital certificates. Digital certificates are electronic certificates used to authenticate an entity and includes a key pair. That helps with securing websites, servers, devices, signatures, and encryption so that you can visit it safely and securely. Public keys are often linked to digital certificates, and this ties into public key infrastructure, which is the framework for handling and managing digital certificates. So it helps with securing digital communications and interactions. Some components of the PKI are certificate authority, which is the trusted third party that signs the certificate, registration authority, which verifies the identity of the entity requesting the certificate, certificate database, which stores it, central directory, which is the storing and handling of cryptographic keys, and then the certificate management system, which manages the digital certificates, and then the certificate policy, which is the online accessible procedures and standards of the PKI for people to be able to read. For the hands-on portion, I will be going over Cryptool, which is a free program or online source for cryptography and cryptanalysis. So this is the website for Cryptool. There is the online version as well as the downloadable versions over here, which I will be going more into depth later. So as you can see, there are a lot of different features and tools that you can use to experiment with cryptography concepts and ideas. As you can see, there's historical encryption, modern encryption, quantum cryptography, and post-quantum cryptography, cryptanalysis, codes, checks, and much more. So for the online version, I will just be going over the Caesar / ROT13. ROT13 is just kind of another version of Caesar, where instead of it's just shifted 13 positions to the right. So let's start. Let's type in some characters. Alright, so you enter your plain text, and then over here are the options that you can choose. As you can see, there's freestyle, uppercase, lowercase, digits, punctuation marks, umlauts, and blanks. So I have lower cases in here, and then with the keys, you can shift it however much you want. So let's say with 2, C should be E, so C is shifting right 1, 2, it's E, as you can see. And then you can just experiment, include however much you want, and then so forth. The key is down here. There's several more features that you can experiment online. Hello everyone, now I'm in the Cryptool application. As you can see, there are many different options. We have the encrypt/decrypt. It includes classic symmetric ciphers. As we see, there's Caesar Route 13 we did earlier. There's the substitution at bash, Playfair, ADVG, ADFGVX. There's the XOR, there's Skytail, and there's symmetric, which there's our C4, triple DES, AES. There's further ones right here. Then there's also asymmetric, and then hybrid. There's also digital signatures PKI. There's a PKI generate, display keys, sign documents, verify signatures, extract signatures, and so on. Then we also have individual procedures, which includes hash, so you can experiment with the different hashes in here. Hash value file, demonstration, and there's so many other different things that you can do here. There's education games, tools that you can do. There's also analysis, tools for analysis. You can look at all these different options here. So to get started, you want to create a file and then new, and then a text box will show up like this, where you can enter any text. I've already entered something. So let's get started with the symmetric classic. We'll go back to the Caesar Route 13. So here it explains everything a bit, and then you can select your variants, options, key entry. So right now it's on Caesar. I'll change it to number value. As you can see, it's a shift of 1, so A becomes B, and then 2 is C, 3 D, and so forth. You can also see it down here as a properties, so it's shifts. Then from this to this, so I'll just change it to 9, encrypt it, then you'll get this text. You can also do it with, let's do it with Route 13. Change Route 13, but for this one, it's a fixed shift of 13, so you can't really change anything. So let's just encrypt this, and we'll go on to symmetric. Let's do RC4. You can specify the bits that you want. Let's do number 4 here. This is the output. You can also go through serpent. Let's do that one. You can specify. Yeah, so there are all of these you can just go through and experiment with. Example, this, documents, generate a session key. And all these you can walk through and go through. I won't go through everything, but it's very useful to learn more about the cryptographic processes. Let's look at the RSA demonstration here. Right, it walks you through and showcases how it's done. So let's go through this for a little bit. We have generate prime numbers. You can generate here algorithms for prime number generation and like the value. You can change all that. Press generate. I'll do it a couple times, and then I'll just use that. So apply that prime, and then there's the parameters, and then you can enter the text. Hello everyone. Encrypt it, and then it'll showcase all these different information for you to go through and learn more about. So yeah, that is my hands-on demonstration of the Crypt tool. I hope you all look into it and experiment to learn more about the different cryptography concepts and ideas. And thank you for watching. So that concludes the hands-on portion as well as the entirety of the video project. I would like to thank everyone who took the time to watch this video. And here are my references that I used throughout the video. Thank you all so much.